Hello everyone, in this video we are going to talk about another set of first order first degree differential equations which are called homogeneous differential equations. Now a first order first degree differential equation is said to be homogeneous if it can be put in the form dy by dx equal to a function of y by x. So whenever we encounter a differential equation which looks like this, then we call it homogeneous, and the procedure for solving such differential equations is that you put y by x as the new variable, let's say v, or you can say y to be equal to vx, so that your dy by dx becomes, since it's a product of two functions of x here, so we apply product rule here, v into the derivative of x, which is 1, plus x into the derivative of v with respect to x. So the old derivative dy by dx gets replaced by v plus x dv by dx, and whenever the differential equation looks like this, it's going to become separable in v and x after we put y by x as v. So let's solve some problems to see how this method works. Look at the differential equation. Let's say we are supposed to solve dy by dx equal to 4x square plus 3y square upon 2xy. Now this is a peculiar setting in which whenever you have a polynomial in x and y above and a polynomial in x and y below, such that the degree of each term happens to be the same all through. Here the degree of this term is 2 because of x squared. The degree of this term is 2 because of y squared. And the total degree of this term, x into y, is 1 plus 1. That's 2 again. So whenever the degree above and below remains the same throughout in the numerator and denominator, such differential equations can always be put in the homogeneous category, because you can take the highest power of x common from above to make it right like this. We can write it like this, and here also we can take x square common to write it as this, so that x square cancels and you are able to put it in the form of a function which looks like a function of y by x. This is always going to happen whenever the total degree above and the total degree below is the same, and that's where homogeneity, the word homogeneity comes in, because there's homogeneity with respect to degree in the terms above and below. So whenever you have degree to be the same all through in the numerator as well as all the terms of the denominator, then you can always put it in this form, so that the substitution, which is y by x equal to v, is going to make it separable in v and x. So let's take y by x as v. This means your dy by dx using the product rule is v plus x dv by dx. Now when we try to write the given differential equation in the v and x setting, then it takes the form, I am replacing dy by dx by its value in terms of v and dv by dx. So that's v plus x dv by dx. And this, you can see, we have written it in y by x format intentionally, because y by x has been chosen as v, so that we can write it as 4 plus 3, y by x is v, so v square upon 2 times v. So now we can simplify it further to make it look like this, because this v goes here, and now simplifying it further, we have x dv by dx equal to 4 plus 3v square minus 2v square upon 2v, which makes it v square plus 4 upon 2v, and it has clearly become a separable differential equation in v and x. So we do it the separable way. We take the terms involving v with dv on one side and the terms involving x with dx on the other side. Integrate both the sides. We can see that the integration of this is quite simple, because we can take v square plus 4 as t or something, so that 2v dv gets adjusted in the derivative. So it's precisely going to become log of v square plus 4, and here you're going to get a log x plus, since logs are involved in the integrals, it's always preferable to take your arbitrary constant also in terms of log, so that you can combine logs in the end to write the answer as v square plus 4 is equal to cx, or since v was chosen by us, V was something that we had introduced in the solution to solve it. So V, by its original definition, the introduction of the variable V was made in this fashion, that V is y by x. So we replace V by y by x again to make it look like this, and that's the final answer to this problem. Let's do one more example to understand this technique better. Look at this differential equation now. Suppose we are expected to solve sine y by x plus y by x equal to dy by dx. Suppose this is the differential equation that we need to solve. Now here you do not see a polynomial with uniform degree above and below. Still, such questions can be handled using homogeneous differential equation procedure, because you can clearly see that here also it's a function of y by x appearing on the right hand side. So primarily it's not polynomial upon polynomial with homogeneous degree above and below which is covered in this category. It is any function which looks like a function of y by x that can be handled using the substitution y by x equal to v, and you can expect it to become separable in v and x once you substitute y as vx or y by x as v. So let's try hands on this exercise also. Let y by x be taken as v. This means your dy by dx is v plus x dv by dx. Replacing the old derivative by the value in terms of new derivative, we have the differential equation taking the form v plus x dv by dx. Here you have sine of y by x, but since y by x has been written as v, so it becomes sine v, and here you have a y by x, so that makes it v. Now simplifying it ahead, you get dv by dx times x is equal to v, cancels out with v, so that leaves a sine v on the right hand side, and you can see that it has become separable in v and x. So whenever we see a function of y by x on the right hand side, dy by dx equal to a function of y by x, it's always going to make the equation separable. If you put y by x as v, then it's going to become separable in v and x always. So let's solve it the separable way. The separable technique is the usual technique. You take terms involving v with dv, and you take terms involving x with dx on the other side, integrate both the sides. So it's primarily the integral of cosecant v, which is log of cosecant v minus cot v, and here you have log of, it's always preferable to write a mod because you're not sure whether x is positive or negative, and since logs are involved, you can take the constant again to be log c so that your answer looks presentable. So the answer takes the form cosecant v minus cot v is equal to c mod x. But since v was introduced by you to make the equation separable, so please do not forget to replace the value of v by its original value, which is y by x, in the final answer. So once you do that, this is what your answer looks like, and that's the end of this category. So I hope you have understood the set of equations which are called first order first degree homogeneous differential equations, and in the next video we are going to cover some differential equations which are not homogeneous to begin with, but you can do something to reduce them to homogeneous. So that's all for now. Thank you so much for watching.